Hi there, we will continue our discussion of the expression evaluation inside PostgreSQL and then later on, of course, also in MongoDB. But it's still PostgreSQL time here. And we've talked about the interpretation, the threaded interpretation, quite efficient interpretation of expressions inside PostgreSQL. But still, if you look at the overhead that comes with the interpretation of such expressions, it has found to be massive. It has found to be very significant in relational database systems. So despite all the implementation and optimization efforts that go into the construction of these threaded interpreters, it's still really significant. The slices of time invested in expression evaluation when it comes to the overall execution time of a SQL query. And to understand that, you just have to think about the number of instructions, the sheer number of CPU instructions that have to be performed to implement the threaded interpretation of a very simple arithmetic expression, like, for example, this multiplication of TA by 2. So this would already involve three instructions of our threaded interpretation or threaded interpreted programs, while it could be maybe two machine instructions, two CPU native machine instructions, if we would have a specific assembly level program to evaluate the same arithmetic expression. So we are a far cry from the achievable maximum speed that a modern CPU could give us for the evaluation of such expressions when we are using threaded interpreters. Inside these interpreters, you will see that the excess of fields, the excess of this A field inside the T row, for example, really is a major burner of time, a major slice of time is being invested in the excess of fields. It happens everywhere. All of our expressions are accessing the fields of the rows. Of course, this is vital in the evaluation of SQL queries, and the time invested into this efficient field access is really significant. And it's really also wasteful, because we would probably perform the extraction of the A field from the T row for each of these T rows, for each new binding of the row variable T again and again. And we would have to discover the same facts about the column A inside these rows again and again. Are these rows nullable? In which position inside the row will the A fields be? Which type do the A fields have? All of this has to be rediscovered again and again for each new row, for each new binding of the row variable T, and that adds up to a significant amount of time spent in the evaluation of expressions and the access of such fields. We would probably find that the expression interpreter follows the same code path through its C code again and again, the same path again and again when it comes to the repeated extraction of the A field, for example. That's what led the designers and the implementers of such SQL-based systems to consider the just-in-time, or JIT, just-in-time compilation of expressions. So if a particular piece of your program, in this case the expression interpreter of your database system, follows the same code path again and again, the so-called hot code path, then it might be beneficial to generate at database runtime, to generate a particular specific piece of machine code that would be geared to just extract, for example, the A field of the current row that is in hand. Embody all the decisions that are to be made to extract the bits that belong to the A field, the checks whether A is nullable, the checks what the type of A is, the checks where A is actually located inside the row. All of these checks, embody them in a particular specific piece of machine code compiled just in time now that we see that these accesses to the field A inside the rows is happening and again and again. And of course, we would have to invest. We would have to invest heavily in the generation and compilation and emission of machine code at query runtime or query planning time. But we would have to do that once only. That is the hope. And then benefit during all subsequent rows, processing of all the rows that are involved in the query. And indeed, such just-in-time compilation, the generation of very specific machine code that is geared to just support the evaluation of one particular expression or maybe even one particular sub-expression inside an expression. This has been added to PostgreSQL since version 11, and I think it has now been switched on by default in version 12. So actually the version that I was using all the time in the course. And of course, we will switch over to the terminal in a second and then see this JIT compilation in action. One more slide on the idea of JIT compilation. The idea is all about turning things that happened at runtime repeatedly. So happen at runtime means extract the A fields from the T rows again and again for each new row again and again. All the decisions that have to be made during this extraction, turn them from runtime decisions into compile time decisions, if this is possible at all. Because we have the schema for all of our tables, we know about the nullability, we know about the types, we know about the position of a particular field already when we compile and plan a query. So these are decisions that could be moved from runtime into compile time. And this is exactly what happens during the just-in-time compilation of queries. The PostgreSQL interpreter is stock full of such decisions because it has been constructed to be very generic, prepared to handle all kinds of error cases and corner cases and overflows, arithmetic overflows, other exceptional cases like the over-allocation of memory or extensions that have been enabled or maybe have not been enabled inside your database system. All of this has to be taken into account by the generic PostgreSQL interpreter, and it leads to a lot of decisions, a lot of branch-heavy routines in the interpreter's hot code path. We will look at the penalty of branch-heavy code inside database systems in an extra section of the course. But for now, let's just appreciate how expensive all these decisions that have to be made during query runtime, and it's the same decisions that have to be taken over and over again. The idea of expression compilation, just-in-time compilation, then is to get rid of these runtime decisions, perform them once, and generate very query-specific code, even sub-expression specific code, native machine code that is being used instead of the interpreted evaluation of these expressions. Let's have a look at the scan fetch sum opcode, for example. So that's the opcode, one of the opcodes that you've seen in the linearized threaded interpreter programs of the last video. If you look inside the code for this scan fetch sum routine, then you will find a cascade, a whole sequence of such decisions that have to be made over and over again, for example, for the extraction of the A field of the current row T. We would check whether this column A is a system column. For example, one of the CTID columns that are provided by the system are not really persistently stored on the pages of our heap files. Is this the case? No, A is not a system column. A is a real stored column. Okay, so let's check whether A is variable length. Would A be probably of char type, or maybe even an array type or something? Something that could be of variable length. If it is, we would have to act accordingly. If it is not, things probably are a bit simpler, and we could follow down this particular path into the execution flow of our scan and fetch sum routine. We would then check whether A is nullable and would then find, okay, A is not nullable. So let's further follow this path down to the part where we can actually perform the extraction of the bits of A from the heap file row. And for each row T, for each access of the A field in the row T, we would have to perform the same sequence of instructions again, perform the same decisions over and over again, and discover that we would always follow the same code path here. Okay. This would be the interpreted non-JIT compiled way of things. The JIT idea would say, if this is the hot code path and it's taken again and again, let's compile the instructions that we need. Let's compile all the logic that we need along this path into one very specific throwaway native machine code routine and invoke that routine when it comes to the extraction of the A field of the current row. So we would generate machine code that embodies the logic along this dotted path, and we would invest the time, probably heavily invest the time to generate this specific machine code and invoke that native machine code routine the next time and all the next times when it comes to the extraction of the A field of the current row. Because the investment into this JIT compilation is really high, we really have to be sure that the investment will pay off later. So we have to avoid investing into JITting, into the whole JIT compilation logic, if the query itself is probably cheap and would not warrant this investment of effort. Okay, so JITting is a complex process, complex multi-step process that will take its time, and we will see a breakdown of this time when we look at the explain plans in PostgreSQL in a minute. It of course involves code generation, so instructions, really native machine instructions or some intermediate representation of these instructions have to be generated along this dotted path that we had identified. Probably we would like to optimize these instructions. Superfluous instructions have been generated. Some of these might be completely deleted. Some of these might be collapsed to be cheaper in the overall execution later on. This optimization effort can be a substantial investment of time when it comes to the generation of this machine code. What we then have is probably some intermediate representation of the machine code that we want to generate. In the case of the low-level virtual machine library, the LLVM library that is in use in many modern compilers, for example in the CLang compiler, but also in use in PostgreSQL now, we would end up with something that's called the LLVM bitcode. This is not directly executable by your native CPU. It would have to be translated and real code for your, say, x86 Intel x86 CPU to be emitted for execution during query runtime. So code generation, optimization, emission, and translation to native code, all of these will take their time, and the whole JIT effort adds substantial overhead to the query planning time of our SQL queries. So SQL query planning time can be substantial already because of optimization effort that we are investing, and the JITting can add substantial amounts of time to this query planning time. And we really have to be careful to not invest in, I'm sorry about that. Okay, here we go again. We really have to be careful to not invest in the JITting of queries that are cheap to begin with. That would probably, where JITting would probably add more overhead to the overall query planning time than we could actually gain. So let's see. Let's consider a very cheap query queue, a cheap query queue whose runtime is actually low in itself already. That would be this cheap query queue. And when I talk about its original runtime, I'm talking about this fraction of time here, this bar of time. That would be the original runtime of our cheap query queue. Okay. Let's assume that JITting has some benefit and it would reduce the runtime of the query by 20%. That would be the middle gray section here. That would be the runtime of the query queue reduced by JITting, JITting by 20%, so only 80% of the original runtime would remain. We would have to invest in JITting, however, and that would be the dark section of this time bar here. Adding this JITting overhead to the 80% of runtime that remains of our cheap query queue indeed adds up to something that would be slower, that would take longer than the original unjitted query. We would indeed find a slowdown of the overall evaluation of this cheap query queue, and all the JITting would have to be invested in vain. We would rather not apply JITting for such queries. All right. Costly queries whose runtime without any JIT optimization is substantial, and that would be that light bar here. They could indeed benefit from JITting. We would, of course, indeed have to invest in JITting again, but we would find a 20% reduction of the runtime of this costly query queue, and that would be the middle gray bar here. Adding that to the JIT time would still lead to some speed up over the original query queue. All right, so this is the speed up we are after. This is what JITting is after, and we would like to have criteria that identify these beneficial queries, these promising queries, these costly queries, before we invest in JITting. Fortunately, the system comes with some estimate of the cost of such queries. The query planning and the query optimizer leaves us with estimate, at least with an estimate of the actual cost of these queries. And we could use that as a criterion to decide whether JITting would be beneficial or not. So let's switch over to the PostgreSQL terminal. There we go. And where I've brought a tiny experiment to demonstrate what's happening with JITting in your original PostgreSQL system. Please be aware that you can only replay these experiments in a PostgreSQL server that has actually the LLVM just-in-time compilation infrastructure in place. So the PostgreSQL server has to be compiled with this particular optimization or this particular option switch turned on, and the PostgreSQL LVM specific libraries have to indeed to be present in the installation directives of your PostgreSQL server. So please be aware of that. Only if these requirements are met, you will see what I'm seeing here in a second, hopefully in my interactive session. So this experiment will revolve around the ternary table. I already brought the original version of the ternary table that has only 1000 rows. This is a tiny table, and querying this tiny table will probably lead to cheap queries, the cheap queries that we've just mentioned on the previous slide. I also brought a larger 2 million row table of the ternary table with me. Evaluating queries, the same queries maybe, over this larger ternary _2m version of the table will lead to costly queries. And we would hope that JITting, investing the JITting effort for expression-heavy queries over this larger table would pay off. All right. So first, let's force JITting off. As I told you in PostgreSQL version 12, JITting is on by default. So let's force it off by now using this option switch. And then look at a query over the smaller table. So that would probably be a rather cheap query. So let's actually plan it and then also execute it. We are using the analyze modifier of explain here, so that we can see how much time is actually being spent in evaluating this query. So let's evaluate that. Okay, this is really very quick. So let's evaluate it again. just to see that there is no caching involved and everything is hot in the buffer. So it's about 1 millisecond of time that is being invested here. Okay, and what we see here is just the normal output that we have seen so many times now that we had when we had to focus on the expression evaluation. This is what's happening regarding expression evaluation. Okay, so now it's time to turn JITting on for this rather cheap query. Okay, so let's turn JITting on like this. Okay, and then let's have a quick look at the parameters at the tunable settings that PostgreSQL comes with that decide whether JITting is indeed probably beneficial or not. And there is one configuration value inside PostgreSQL. That's the JIT above cost value. And the JIT above cost value says that any query whose cost is estimated to be over 100,000 cost units, whatever, space dollars, whatever that means, any query that is estimated to be costly beyond 100,000 units, this query would undergo JITting. There is another switch, actually there's many switches. Let's not look at all of them, but let's look at some of them. The JIT optimize above cost switch, let's no show, not set show. That says we will only invest in the really heavy, in the really costly optimization of our JIT programs if the original cost estimate for our queries is more than 500,000 units. Okay, so the system is really very defensive here. Only queries that are supposed to be super expensive anyway, they would undergo JITting. So now let's be silly for the next few minutes and set these parameters to ridiculously low values, to just a value of 10. That means that probably any query whatsoever will undergo JITting, and that's probably not a very clever thing to do, because the effort for JITting would probably not really pay off for these cheap queries. All right, so now JITting will happen. And let's consider the same query again. Again, the cheap query over the small table. Now with JITting forced on. Okay, let's be fair, evaluate multiple times, 3 times maybe. All right, so we are seeing execution times of about 50, 60, 70 milliseconds here, which is way worse than what we've seen with a 1 millisecond in the case where the JITting was turned off. All right, let's look at the plan. The plan looks, it's a sequential scan over the ternary table, and the output will still be these 3 arithmetic expressions, but we will also see JIT specific information here. And as you can see, indeed, expressions have been compiled using the JIT logic here. All right, optimization has been performed. The very costly optimization has been performed. Also, the deforming has been performed, has been JITted. Deforming is actually the excess of particular fields inside rows. So all of these aspects of the expression compilation have indeed been JITted and turned into native code. And this took some time. Look at the optimization effort that has been invested, like 26 seconds, or the emission of code that has been invested, like 30 seconds. If all of this is being added up, JITting took about 58.4 milliseconds. The overall execution time of this query has only been 59.5 milliseconds. So almost all of the time, 99% of the time has been invested into JITting. And that led us to this ridiculously slow execution time. So all of the JITting took all of the time, and we had actually no chance to really benefit from all the effort that was invested. Sad. Okay, things look different, hopefully, when we turn to more complex queries. So first, let's switch the JITting off again. And now look at the same query, the Q6 probe query over the ternary 2 million row table. All right, this will be a more costly query, and many more expression evaluations will happen when we perform this particular query. With JITting turned off, let's see how long the execution time is. Okay, take some time. Okay, so 3.3 seconds. Let's come again. 2.6, one more time. Okay, 2 seconds. I don't think that we will get much faster here. Okay, 2.9. All right, so that's probably in that particular array between 2 and 3 seconds. Again, this machine is super busy with video encoding. This will probably explain the fluctuation in time that we are seeing here. All right, so let's take a record of about 3 seconds that this query is using without JITting. So now let's turn the JITting back on. And as you can see, I'm a bit more sensible, a bit more reasonable now when it comes to these above cost setting, JIT above and JIT optimize above cost setting. They are set to 10,000 now. I think the query that we are looking at has a estimated cost of more than 10,000. Indeed, it has an estimated cost of 78,000 and more. So using these parameters looks reasonable, somewhat reasonable, and it will lead this rather costly query to be considered for JITting. JITting turned off with these settings. Okay, now let's plan and then execute this query again with JITting turned on. Okay. Okay, so we see execution time of about 1.8 seconds, which is an improvement already over the execution time of the 3 seconds that we have observed without JITting. Okay, and as you can see, the generation of JIT code indeed took its time again. The optimization took its time, the emission took its time. All of this added up to 100 milliseconds. All right. But this was a beneficial investment that can that will be added to the overall execution time of the query. But we benefited so much from the native code that has been generated while we were executing the many evaluations of these arithmetic expressions that all the effort paid off, leading us to an execution time that is faster than with JITting turned off. Okay, so that's the trade-off. The trade-off that we have to very carefully consider whether JITting is something that we should consider. But if we tune these parameters correctly, then there is some benefit to be had. So there's indeed expression, interpretation, and compilation inside a relational database system. That's super interesting. Let's reset all of these parameters to their sensible default values so that I'm not surprised on the next runs. And that's about it. That's about the expression evaluation inside PostgreSQL. MonadDB has something to offer there too, and we will look at that in the next video. I hope to see you there. Bye-bye.